হ্যালো হ্যালো
হ্যাঁ অমিত দা সবাই আছে।
বলছি ভিডিওটা অফ করলেই যেন বেরিয়ে যাচ্ছি মিটিং থেকে।
না বেরোচ্ছেন না তো, আছেন আপনি থাকছেন, সবার আসলে ভিডিও অফ তো ওই জন্য, মানে আপনারা কেউ একজন অন করে রাখুন।
হ্যাঁ সেই প্রবলেমটা আমারও হচ্ছিল, মনে হচ্ছিল যেন আমি
না না আছেন।
হ্যাঁ ঠিক আছে। আমি একটা মেসেজ করেছি সবাইকে ভিডিও আর অডিওটা অফ করার জন্য পার্টিসিপেন্টসদের।
এখনো তো কেউ ঢোকেনি, এখন মেসেজ করে কি হবে? যারা ঢুকবে তারা পরে ঢুকবে, তারা একটা মেসেজ।
অমিত ঢুকেছে।
আরে খুব জোর একজন দুজন, তার বেশি তো নেই।
হ্যাঁ বলছি কি, হ্যালো, আপনারা কেউ না ভিডিওটা একটু অন করে রাখুন, অনিন্দিতা দি বা অমিতা। কারণ হচ্ছে আমি তো এই লাইভ স্ট্রিমিংটা করছি, তো যতক্ষণ না মানে আপনারা ভিডিও অন করে রাখছেন ততক্ষণ কিন্তু লাইভ স্ট্রিমিং স্টার্ট করতে পারবো না। হ্যাঁ কেউ একটা অন করে রাখুন।
হ্যাঁ করেছে অমিত।
ঠিক আছে আমি তাহলে করছি।
ভিডিও অন করার তো ম্যাম অপশনই পাচ্ছি না।
ম্যাডাম শুনতে পাচ্ছেন? হ্যালো
হ্যাঁ বলুন। বলুন, শুনতে পাচ্ছি।
এটা দেখে নিন ঠিক আছে কিনা এটা।
হ্যাঁ হ্যাঁ ঠিক আছে, একদম ঠিক আছে, আমি
ঠিক আছে
দেখে
তো?
নিয়েছি। হ্যাঁ হ্যাঁ
টেলিং গুলো সব দেখে নেবেন একবার।
হ্যাঁ একদম ঠিক আছে।
হুম।
ঠিক আছে, একদম ঠিক আছে। প্রফেসর এন্ড হেড ডিপার্টমেন্ট অফ ম্যাথমেটিক্স, ন্যাশনাল ইনস্টিটিউট অফ টেকনোলজি, রোড। ঠিক আছে, একবার হ্যাঁ এই স্যারেরটা একবার পড়ুন, একবার অশোক নন্দা স্যারেরটা একবার পড়ুন। অশোক কুমার নন্দা, প্রফেসর, ডিপার্টমেন্ট অফ ম্যাথমেটিক্স এন্ড স্ট্যাটিস্টিক্স, ইন্ডিয়ান ইনস্টিটিউট অফ সায়েন্স এডুকেশন এন্ড রিসার্চ। একদম ঠিক আছে।
আনমিউট করলে কতক্ষণ যাবে?
গৌরীদা, গৌরীদা,
হ্যালো অমিত।
হ্যাঁ শুনতে পাচ্ছ তো?
হ্যাঁ 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 শুনতে পাচ্ছি শুনতে পাচ্ছি। হ্যাঁ শুনতে পাচ্ছি।
হ্যাঁ সুব্রত।
সবাইকে একবার চেক করে নে অমিত।
হ্যাঁ হ্যাঁ
হ্যাঁ স্যার আমাদের সুখদেব দা এসছে কি? আমরা তো দেখতে পাচ্ছি না বোধহয় সুখদেব দাকে।
না, সুখদেব বাবু এখনো ঢোকেননি।
আমি
জয়দীপ দা
উপস্থিত।
আচ্ছা আচ্ছা, হ্যাঁ ঠিক আছে ঠিক আছে,
সুব্রত আছে কিন্তু।
হ্যাঁ দেখেছি।
রয়েছে, শোনা যাচ্ছে?
সুব্রত ভক্ত।
শুনতে পাচ্ছ?
হ্যাঁ
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 শুনতে পাচ্ছ?
হ্যাঁ
ঠিক আছে,
একদম।
ঠিক আছে।
আচ্ছা। না আনমিউট ছিল তো সেজন্য দেখে নিলাম।
অমিত
হ্যাঁ,
সরকার কি
ঠিক
এসছে?
আছে।
অমিত
না, ও
অমিত
পরে ঢুকবে, ও
সরকার
পরে
এসছে। অমিত সরকার
পরে আসবে।
একটার সময় আসবে একটা।
অমিত সরকার, আচ্ছা আচ্ছা।
কৌশিক দা শুনতে পাচ্ছেন? কৌশিক দা, ডক্টর কৌশিক ঘোষ।
মিউট করার আছে, আনমিউট।
আনমিউট করা থাকলে শোনা যাবে তো।
হ্যালো
হ্যাঁ এই তো
হ্যালো।
আছেন।
হ্যাঁ হ্যাঁ
হ্যাঁ হ্যাঁ আছি আছি।
হ্যাঁ, বলছি শান্তনু দা তো আপনাদের ব্যাচমেট না?
হুম শান্তনু আমাদের
হ্যাঁ,
ব্যাচমেট।
হ্যাঁ ঠিক আছে।
অনিন্দিতা, রিয়া এরাও আছে।
হ্যাঁ হ্যাঁ ম্যাম আছি।
হ্যাঁ হ্যাঁ দেখতে পাচ্ছি।
আমাদের থার্ড ইয়ারের দুটো মেয়ে দেখতে পাচ্ছি।
দীপিকা আছে, দীপিকা।
দীপিকা দেখেছি, ঠিক আছে। আস্তে আস্তে সবাই ঢুকুক, সুখদেব বাবু করে দেবে।
হ্যালো হ্যালো।
মিউট হো না।
সরি।
হ্যাঁ স্যার, সুখদেব স্যার শুনতে পাচ্ছেন তো? সুখদেব স্যার, সুখদেব স্যার শুনতে পাচ্ছেন?
হ্যাঁ শুনতে পাচ্ছি অমিত।
আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে।
হ্যাঁ ওকে আছে। দেখা যাচ্ছে তোমাকে। এখন তো মিউট আছে।
मैं बोल रही हूँ
Sir, requested keep microphone off. This is absolutely necessary. Please keep the microphone off. A feedback is coming. Please mute your microphone.
হ্যাঁ অনিন্দিতা ঠিক আছে? হ্যালো।
হ্যাঁ হ্যাঁ হ্যাঁ, শুনতে
হ্যাঁ
পাচ্ছি।
স্যার, হ্যাঁ হ্যাঁ স্যার শুনতে পাচ্ছি আপনার কথা।
হ্যাঁ 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 শুনতে পাচ্ছি। ওকে ওকে প্রসিড অন। হ্যাঁ
স্যার 5 মিনিটস আসলে বাকি আছে, ওই জন্য আমরা একটু ওয়েট করছি।
ঠিক একদম প্রপার ইয়েতে করো।
আচ্ছা ঠিক আছে। হ্যাঁ স্যার।
ঠিক আছে, আমার কথা শুনতে হবে, এখনটা মিউট হয়ে গেছে দেখছি।
স্যার আপনিও কিন্তু মিউট করেই রাখবেন, না হলে ফিডব্যাক আসবে, আপনি ভালো শুনতে পাবেন না। যখন আপনি কিছু বলবেন তখন ওটা আনমিউট করবেন।
ଶୁଣା ଯାଉନି କଣ ପାଇଁ?
ম্যাডাম, হ্যাঁ বলছি প্রিন্সিপাল স্যার এসেছেন?
আমি তো লিস্টে দেখিনি, পার্টিসিপেন্ট লিস্ট স্যারকে একটু ফোন করে নেবো নাকি?
গার্গি আছে? গার্গিকে একবার জিজ্ঞেস করলে হয়। স্যারকে একবার ফোন করে নিন, তাহলে স্টার্ট করা যায়।
আচ্ছা, তাহলে কি আপনি ফোন করবেন, আমি স্টার্ট করবো না ফোন করে নিই? তাহলে ঠিক আছে, দাঁড়ান ফোন করে নিই, তাহলে দাঁড়ান। Sir, are you there? Principal sir, are you there? Sir, you are not audible. Yes, sir. Yes, sir. Yes, sir. Yes, sir. You are audible.
হ্যাঁ, আর আপনার দেখতে পাচ্ছি না তো, স্টপ ভিডিও এই যে নাও। ঠিক আছে, সুখদেব বাবু।
হ্যাঁ স্যার বলুন স্যার।
বাবু, গুড মর্নিং। গুড মর্নিং।
মর্নিং স্যার। আবার কে পে
আবার কেটে গেল কেন?
করছি।
স্টার্ট করুন।
হ্যাঁ হ্যাঁ।
আচ্ছা স্যার। হ্যাঁ স্যার। স্যার প্রিন্সিপাল স্যার, স্টার্ট করছি। হ্যাঁ
একদম একদম। হ্যাঁ
হ্যাঁ, শিওর, প্লিজ।
Please, I'd like to remind all the participants, don't keep your microphone and video on. Please don't keep your microphone and video on during webinar. This is our request. Amit, please send the message to the chat box.
Okay.
Okay. So let me start the webinar. A very good morning. On behalf of the Department of Mathematics at Anandaram Joypuria College, I, Dr. Anindita Basu, as a convener, take this honor to welcome our distinguished speakers, delegates, research scholars, and students across India participating in the national webinar on applications of mathematics. This one-day webinar is organized by the Department of Mathematics in collaboration with IQAC of our prestigious College of Kolkata. Let me start the webinar with a prayer of Rabindranath Tagore. Bipode more raksha karo, eno he mor prarthana, bipode mora na jano kori bhoy. Which means, I do not pay to protect me from all odds. Let me be fearless. Power in the present pandemic scenario, which has brought countries to a scale requiring to hold scientific research activities as webinars. Amidst the present partial or full lockdown, when we are away from our academic institutions for over past 4 months, we have been relentlessly trying to connect with the brilliant minds of our academic world using various online platforms. This webinar could not have been held without two eminent mathematicians as the speakers, able guidance of the members of IQAC, and enthusiastic participation of all of you. In our effort, a strong source of motivation and inspiration for us is our principal, sir, Dr. Ashok Mukhopadhyay, who showed a very keen and active interest in this webinar and guided us to organize it. I take
বলো
শোনা যাচ্ছে না তোমাদের কথা। হ্যালো,
আচ্ছা শুনতে পাচ্ছি।
ও
ম্যাডাম,
অনিন্দিতা কি বললো? I could not get the cue from Anindita.
ম্যাডাম, অনিন্দিতা ম্যাডাম। Madam, you are not audible. Anindita madam, you are not audible.
Amit, you request principal to start the program.
Okay.
Okay. তুমি request করো principal.
please start the program. Sorry, I was disconnected.
Oh, yes. Anindita will come.
Sir, please proceed.
So very good morning. I welcome this particular endeavor by the Department of Mathematics, and I particularly welcome Dr. Ashok Nando from IIACR and Dr. Shantanu Shaha from NEET Rourkela, and our departmental colleagues, the senior teachers, Dr. Dotto, and all other faculty members are present. I express my gratitude. I welcome you that in this hour of crisis, you are trying to uplift the academic environment of this institution, and you are in fact encouraging us to contribute something to this society. Well, today's webinar is regarding of application of mathematics. I'm not sure about the details of the thing, but I am not from mathematics arts. I am from commerce stream. We have some pretty linkages with mathematics, and what we understand and what clouds my mind, that there are many objects and there are many concepts that exist in mathematics which do not exist in reality per se. The particularly a particularly concept I'll be talking about, which is very much associated with our subject commerce, accounting also, that is point. We know that points do not exist in reality. The scientists, the mathematicians, you all know that points do not exist in reality. But even it is, the entire geometrical sciences and the entire universe is dependent on your concepts. So the lesson is that never had been in our history the world of science or the knowledge of science was in standstill. It is a continuous process and progress. Think about the Pythagoras, who was disproved by his disciple Hipparchus. Think about the Fermat, who was disproved and challenged by his next generation mathematician. I'll be particularly interested, and I would be indebted to share my views and my respect to one great mathematician at least, who is father of our subject in accounting too, that is Luca Pacioli. And I talked about my particular interest with Anindita Basu when giving up introductory talk to this particular webinar. Sir, we all know that probability was, it is shaped in the hands of Fermat and Pascal sometime in 1650, some 200 years back. Before that, we came in the writings of Cardano. Before that, in 1494, Pacioli took out his seminal book on the Summa di Arithmetica Geometria, which is very much within our purview of our study. We start from Pacioli, in fact, in accounting. And Pacioli mentioned about the questions of probability, though his answers were wrong. Some 200 years after, 100 years, 150 years after the things were proved. So it again proved that it was never in standstill, it was a continuous progress. And even if it is said that Pacioli was dependent on Fibonacci some 200 years back in 1200 something, and his book was based on Fibonacci. Sir, I would also like to share my thought that Pacioli took the limelight, Luca Pacioli took the limelight because of the development of printing and not in the development of mathematics. Sir, we had in our times Raghunath Shiromani of Navadvip, we had Vallabhacharya of Champaran, all were contemporary to Luca Pacioli or even Nilakanto. So with these small and some points and with this some inspirational talk, I would like that we will be having a very interesting discussion. And why I come to this particular point of Pacioli and others, because you was very much interested in the application of mathematics before the Renaissance time. I mean, in the Renaissance period, he wanted to regenerate and read and re-establish and republish the knowledge which was in stock for last 200 years. To conclude, I will give you a particular clue that, sir, nowadays a transdisciplinary subject mathematics should help and become a transdisciplinary subject, and especially the cryodynamics, what we are talking about. And we are hungry to know that the history and the events of evolutions will be analyzed by the mathematicians, and they will predict the future pattern of the society, the future pattern of the universe, the future pattern of the mankind. And we look forward to this, that the mathematicians all over the world will go for an interdisciplinary work. They will support and they will analyze, when history will be analyzed in the light of mathematics. With these 2-3 words, I would like to conclude my introductory talk, and my respect to Professor Ashok Nando from IISER and Professor Dr. Shantanu Saha from NIT Rourkela, who may be talking about the intricacies of the very particular things which is within the subject of mathematics. But I know at the end, you must give some hint, you must give some predictions or some sort of suggestions where we can assimilate our knowledge and not disseminate. Thank you very much. Thank you, all my colleagues and all the participants who have joined this program. Thank you very much, sir.
Thank you, sir, for sharing your nice thought and inspirational words. Thank you very much, sir. Now we are going to proceed to our technical sessions. This webinar is basically focused on the application of mathematics in different aspects. Today we have with us two renowned mathematicians, Professor Ashok Kumar Nanda from Indian Institute of Science, Education and Research, Kolkata, and Professor Shantanu Sahare from National Institute of Technology, Rourkela. I am honored to welcome both Professor Nanda and Professor Sahare in our webinar and express my heartfelt gratitude to them for accepting our invitation and making this event successful. We all are eagerly waiting for the lectures to be delivered by them. Before that, I personally take the opportunity to share with you all that I have been a student of Professor Nanda in IIT Kharagpur, and he has been a famed philosopher and guide for almost all research scholars, including me. Thank you very much, sir, for being with us. Now, I may please invite Dr. Amit Kumar Pal, Head Department of Mathematics and convener of the webinar, to kindly host our technical sessions. Dr. Amit, please.
Thank you, Dr. Anindita Basu, for such a wonderful introductory session, which tune our today's program. I also thank to our respected principal sir, Dr. Ashok Mukhopadhyay, for his wonderful motivated talk, which means a lot for us. Now come to our goal to today's national webinar. Before that, once again, I heartily welcome to our respected distinguished speakers and also to all our participants. Now, for technical session, our first distinguished speaker is Professor Ashok Kumar Nanda, a professor of IISER Kolkata. Before that, I just want to present a brief biography of Professor Ashok Kumar Nanda. Professor Ashok Kumar Nanda is currently a professor and former head of Department of Mathematics and Statistics, National Institute of Science, Education and Research, Kolkata, India. Professor Nanda completed his bachelor's degree in statistics honors from Ramkrishna Mission Residential College, Narendrapur, and master's in statistics from Calcutta University. He completed his PhD from Punjab University, Chandigarh, India. He also completed his postdoctoral research work from University of New Brunswick, Canada. He has huge 30 years of teaching experience with different universities and institutions of national and international repute. Some of them are Punjab University, University of Arizona, USA, Indian Institute of Technology, Kharagpur, and now at present, IISER Kolkata. He has published near about 100 peer-reviewed research papers in numerous fields and various international SCI journals of repute. He has contributed papers on several topics such as reliability, survival analysis, maintenance and replacement, and entropy. Under his sole supervision, 7 research scholars had been awarded with PhD degree and 1 postdoctoral scholar completed. Also, he is now supervising 2 more PhD scholars and 1 postdoctoral fellow at present. He is associated editor in the journal Communications in Statistics, Simulations and Computation, Taylor Francis since 2009. Also, he is associate editor of the journal Communications in Statistics, Theory and Methods, Taylor Francis since 2009. He is associate editor of the Journal of Indian Statistical Association since 2010. Also, he is a board member of Rashi, a journal of the Society for Application of Statistics in Agricultural and Allied Sciences since 2018. Professor Nanda has also membership of or fellowship of different learned academic accredited bodies such as Society for Application of Statistics in Agriculture and Allied Sciences since 2016, International Indian Statistical Association since 2007, National Academy of Sciences, India since 2002, Indian Statistical Association since 2001, Indian Association for Productivity, Quality and Reliability since 1996. With all these kind words, I want to invite Professor Nanda to deliver his speech. Sir, please, sir.
Thank you, Professor Paul, for nice introduction. Good morning to everyone. I must thank the organizers of this webinar, especially Professor Ashok Mukhopadhyay, the principal, and Professor Anindita Basu for organizing this and inviting me for giving one talk in this webinar. Now I would like to share my screen with everyone.
Full screen mode, please. Full screen mode হয়নি এখন।
Screen হয়নি?
না। আরেকবার বন্ধ করে নয়।
দেখছি।
হ্যাঁ এবার হয়েছে স্যার।
ঠিক আছে।
Absolutely.
The title of my talk is Shannon Entropy, Some Drawbacks and Remedies. We know Shannon entropy, but here I will give little bit of genesis first, then some basics of entropy, and then probably I will go for this derivation of entropy from the postulates. We'll see what are the postulates Shannon gave, and other postulates as well from where Shannon's entropy can be derived. Some other entropies also we'll discuss related to Shannon entropy, but definitely this list of entropies, whatever we will be discussing here, is not exhaustive. There could be quite more different kind of entropies available in the literature. Some we will discuss here. Then so far, whatever we have done, that will be on discrete part. If the random variable is continuous, how to define entropy? We'll do that after discussing different kinds of entropies. Then we will discuss different use of entropy as a measure of tail heaviness of a distribution, along with the problem with the kurtosis measure as pickettness. Then we will come to this drawback and remedies. Shannon entropy tells how to define entropy of new item. If some item is used quite some time, how to define entropy for that, we'll discuss this. Then we'll come to different kinds of modifications available in the literature. And we'll stop after telling one problem, very interesting problem, that probably those who are interested in entropy can think of the solution. Here on the screen, you can see a couple of pictures. The first one, this is our Rudolf Julius Emanuel Clausius, who is a German physicist and mathematician. He is one of the founders of thermodynamics, and he coined the term entropy. Whatever we are telling as entropy, this term is actually coined by Clausius. He used this idea of entropy around 1850, but the term he coined sometime in 1865. The etymologists think that probably the idea of Clausius for taking this particular term entropy could be from the Greek word entropin, which means energy turned to waste. Since Clausius used entropy in thermodynamics, this is definitely some useful term for him, because we know that no reaction is 100% efficient. And as a result, when some energy is transferred to some other energy, then there will be some energy lost or dissipate as heat. So this is actually this energy turned to waste. That's why the term probably was coined by Clausius. This is the idea of etymologists. After Clausius, you see here the three people. Here it is Ludwig Boltzmann, then James Clerk Maxwell, then Josiah Willard Gibbs. They eventually gave the statistical basis to entropy. And these two names, first to Boltzmann and Maxwell, probably are very familiar to mathematics people, especially physicists are very much well known to their work. Specifically in statistics and mathematics, we use Maxwell-Boltzmann statistics. Physicists, quite obviously, physicists use this a lot. Maxwell-Boltzmann statistics, then Bose-Einstein statistics, Fermi-Dirac statistics, all those stuff. This is Shannon, what we are going to discuss today, Shannon's entropy, Claude Shannon. Sometimes this entropy is called Shannon-Wiener entropy because Norbert Wiener, he, on the same year in 1948, when Shannon entropy was, Shannon worked on entropy, the same year, 1948, Wiener published one book, Cybernetics. This term was also coined by Wiener in 1948. Sometimes people call it Shannon-Wiener entropy, but mostly people know this entropy as Shannon entropy. And Shannon used this entropy in information theory. Wiener also did that independently. We'll come to this entropy. This term is your Merriam-Webster's dictionary tells this degree of disorder or uncertainty in a system. And this is eventually the book Cybernetics, published by Wiener. And the same time as it is written that this mathematical theory of communication, this was the first paper published by Shannon on entropy in 1948 in Bell System Technical Journal. You see this picture here, you will see that this one is just see the hair and this hair. Clearly we say that here it is more entropy of this hair and here it is less entropy. To understand this little bit, we have to go to again physics. Because in physics, the thing is like this, according to some law of thermodynamics, a spontaneous change results in an increase in entropy of the universe. And obviously, it is like this, that every system is expected to evolve into states with higher entropy as they approach equilibrium. That means every state has your higher entropy in the equilibrium, because once it goes below this or deviates from equilibrium, its entropy will be less. And every system, by nature, everything tries to get maximum entropy. If the system is isolated, then the system's entropy reaches its maximum whenever there is equilibrium. This isolated system is very important, because if the system is not isolated, say for example, if heat is transferred from the system to the surroundings, then it is quite possible that this particular system we are talking of may have your less than the maximum entropy, but it is in equilibrium. This is because when heat leaves the system, then it goes to the surroundings, and in this case, taking surroundings and the system together, if you see, then obviously this will have the maximum entropy. People mostly are interested to know the type of entropy we'll be discussing here. This is information related entropy, but Clausius started that with your thermodynamics entropy. People mostly think, is there any relation between the two? Yes, there are relations. And this is one very nice book. Those who are interested to know the interrelations between the two kinds of entropy, they can probably go through this book. The title of the book is A Farewell to Entropy, Statistical Thermodynamics Based on Information. This farewell to entropy, I have marked it in a different color, because in the book, this book is really very nicely written. Because if someone wants to get some good flavor of entropy, probably this will be one of the best books I can think of. But somehow this Ben Naim has advocated, as he has given the name here, farewell to entropy. He is not in favor of the term entropy. he is telling that probably some information or something could be good in place of entropy, because entropy may be good for your thermodynamic entropy, but as when we are coming to your information science, probably this is not the good term. This is he has given different kinds of argument in favor of this. But anyway, I don't think that it is a personal view that it is not really necessary that we have to parallel the particular term entropy, because all of us know that we are using your random variable from your in different places. And if we see the definition of random variable, the random variable is neither really random nor it is variable. So I don't think that it is really necessary to remove the term entropy, because people are very, acquainted with this particular term entropy. But anyway, those who are interested probably can go through this particular book. Information transmission takes place through different ways. Different ways means probably when we read newspaper or we read book, when we talk on phone, then something I am telling, and someone who is receiving the phone, probably he's getting some idea of what I am telling, or the other way. Listen to TV. When we listen to TV, it may be news or anything, some information is coming from there to us. Attending some lecture or delivering some lecture. So when we attend some lecture, then some information we are getting, which probably we do not know. During the deliver of a lecture, probably some people will give some idea. So the speaker probably will get some idea. So this is the new information to him. So what we see is that the information is carried over from one place to another through different ways. So we seek information when there are more than one alternative. Obviously, if there is just single possibility, then we don't have any uncertainty, and we are certain about the outcome of the event, that this is going to happen, because this is the only one possibility of happening that particular event. For example, whether tomorrow will be a sunny day or a rainy day, that really we don't know. It could be a sunny day or it could be a rainy day. So since we don't have any information, then once tomorrow comes and we see that whether it is sunny day or rainy day, then we will get the information what we didn't have at the very beginning. So if an event occurs in just one way, that we have already told, there is no uncertainty and no information is called for. So we get information by the occurrence of an event. So information received by occurrence of an event should be same as the amount of uncertainty prevailed before its occurrence. This is quite clear. Here we will give some little bit of idea of this entropy in information science. Suppose there are different inputs here, A1, A2, AR. We are giving different inputs, and there is some information channel. And here we are coming as these are the things we are getting as output. So A1, A2, AR we are sending. In the output we are getting B1, B2, BS. You see that R need not be equal to S. So that will be clear from some channel matrix. This BJ, we are given that AI, that means I am sending some information, AI information, and I am receiving the information BJ. So there is some change in between in the black box. And this probability I am telling PJ given I. So this is the your channel matrix. So probability that I am sending A1, but I am receiving P1, a B1 with probability P1 given 1. Similarly, I am sending A1 and I am getting B2 with probability P2 given 1, something like this. So once I am sending this A1 can be reproduced to the receiver as B1 or as B2 or as BS with a different probabilities. So obviously this row sum should be your 1. That's what we have written over here. So every row sum of this channel matrix should be 1. A channel is called symmetric if the channel matrix is symmetric, which is quite clear. It is binary if the channel matrix is 2 by 2. This is something important. A channel is called a noiseless channel if the matrix has one and only one non-zero element in each column. So you see here in each column, if I have only one non-zero element in every column, then this channel is called noiseless channel. The question is why? Why it is noiseless? That will be clear from here. You see, suppose this is the channel matrix and A1 I am sending and I am getting here B2. A2 is going to be B2 with probability half. I am sending A1 and I am receiving this as B2 with probability half. That means A1, A2 I am sending and I am receiving B2 with probability half and half. That means A1, A2, they are mixing up when they are coming to me with probability half and half. That's why there will be some noise. But if I come here, you see in this particular channel matrix, we have only one non-zero element in each column. So A1 will go to B1 with probability 1, so there is no problem. A2 can go to B2, or A2 can be converted to B2 with probability half, and it may convert to B3 with probability half. That means once I am sending A2, it can be B2 to me, or it can come to me as B3. So only anyone will come. So there will be no noise in the system. That's why this is the name, noiseless channel. Here I will give a couple of applications of your entropy in different fields. In physical science, there are. It is not that this is the only paper or only book using your entropy in physical science. I have given only one. So you can see that it has been used in physical sciences. It has been used in communication theory as well by Shannon. It has been used in language also again by Shannon. It has been used in biological sciences. It has been used in information theory. It has been used in pattern recognition. It has been used in fuzzy analysis. Also in social science also we have seen use of entropy. In economics also, in finance also we have seen. So there are many more. In different fields, people have used entropy. Here is one book. It is really very good book again, which has given different aspects of entropy, and very lucidly written book by Cover and Thomas. Now let us see one particular example and try to understand how this entropy is coming. E is one event that you will get a job. Suppose probability of getting this job is my P. Now let us see this. If P is 0.01, that means probability of getting the job is very less, and some friend is giving this information to you that you have got this particular job. You know that your probability of getting the job is very less, but still you are getting, and you have got this information from your friend, then probably this will be your reaction. You will tell, hooray, oh, I didn't expect really to get this job, but somehow I have got it. But if you know that this probability is very high, then whenever I will tell you that, oh, you have got this job, you say, oh, okay, thanks, because I was almost sure, because the probability is 0.99, so I was almost sure to get the job, something like this. So it says that when probability is very large, then we have less information. This particular occurrence of the event will contain less information. And if probability is very less, then eventually some substantial amount of information will be there with occurrence of that particular event. This tells that entropy should be a continuous and decreasing function of P. P is my probability. So if H denotes the entropy function, then HP should be a decreasing function of P. Suppose two events E1 and E2, they are independent. Then this P1, P2, H of P1, P2 is the occurrence of both the events together. And this should be your H of P1 plus H of P2, because this is the occurrence of P1 and this is the occurrence of P2, entropy of occurrence of P2. So this is your, this entropy and this entropy, once you add, then this should be your total entropy or total uncertainty, whatever we had before the occurrence of these two events. The occurrence of a sure event does not give any information, because I know that this is going to happen. So probability of this certain event. So H1 should be your 0. Now we are transforming this. P I am writing as a to the power minus x with some a positive. Then HP will be h of a to the power minus x. I am calling this as phi x. This is a function of x. Then I am transforming from h to phi, and this will be that phi x should be a continuous function in x. Phi x1 is less than equal to phi x2 for every x1 less than equal to x2. Phi x1 plus x2 should be phi x1 plus phi x2, and phi 0 should be 0. So with those your postulates, we'll see how Shannon entropy comes. Let x be a positive integer. Then from here, phi x1 plus x2 is phi x1 plus phi x2. Using that, I can write that phi of m should be m times phi of 1. So I will just simply, I will write 1 plus 1 plus 1, something like this. Then I write m as n times m by n, then this phi m can be written as m by n plus m by n plus m by n times. So once I write this n times, then immediately I can write it n times phi m by n, again by this postulate 3. So this gives phi m by n is 1 by n phi m. I am taking n to this side. So this is your m again will come out because of that. So it will be m by n phi 1. So what we get? We get phi x equal to x times phi 1 for every rational x. And a positive rational, of course, positive rational x. Now I am taking some y as some positive irrational. And from the denseness property, we know that there exists a sequence, a rational sequence converging to this y. That is known. This comes from the dense property of real numbers. And phi we have taken to be continuous. So once phi is continuous, I can write y here. I can write here y as your phi of limit of xn. And being continuous, I can take the limit outside. So once I take this limit outside, then phi xn again can be written as xn phi 1, because this result is true, because we have seen that this is true for all rational numbers and xn is my rational. So I can write this like this, and limit of xn is eventually my y, so I can write it y times phi 1. So what we get, this result is true for rationals, this result is true for irrationals. That means phi x is x times phi 1. This is true for all positive irrational number from here. So combining the two, I can tell that your phi x equal to x times phi 1 for all real x. So phi x is x times phi 1 for all real x. I call this phi 1 as some constant c. Okay. Now we will go back. So we had phi hp as my phi x. So phi x I have seen is x times c. So this is your minus c times, just what is x? X is from here minus log p base a. So hp is coming out to be this thing, minus c log p base a. So we can take any constant over here. So without any loss of generality, we take c equal to 1 and a equal to 2, so that hp comes out to be this. In mathematics, we generally don't use log 2. We take your natural logarithm. The reason is very simple, because once we transform this to natural logarithm, this is just some your constant multiple of this. So there is no problem if I write this a constant multiple. Now you see that occurrence of one event E, once we receive information on E that HP, or it could be H1 minus P, that if E is occurring, then entropy is HP. If E is not occurring, then this is H1 minus P. But before the occurrence of the event E or E complement, we really don't know which one is going to occur. So the expected information received because of this event E, or I can say that from this probability vector P1 minus P is your H into HP, P into HP plus 1 minus P into H1 minus P. So this is the expected information coming out of this event E. So if here is my probability has your probability vector has two things, P1 minus P, because I have only two things possible. One is occurrence of E or non-occurrence of E. If there are different n events with probability vector P1, P2, Pn, that means this is my probability of E1, this is my probability of E2, this is my probability of En, something like this. Then the entropy corresponding to P will be the expected entropy. I will just sum up Pi, HPI, and this is coming out to be this. I have just put the value of HPI over here. This is with sigma Pi equal to 1 and Pi positive. This is what is actually your Shannon entropy. But okay, before telling that, let me tell something about this thing. Given the constant Pi in 0, 1 with sigma Pi equal to 1, this HP1, P2, Pn, whatever is given over here at sigma Pi log Pi, will simply maximize it subject to this constant sigma Pi equal to 1. Then we will see that maximum value is coming out at 1 by n, 1 by n, 1 by n. That is, all Pi should be same. This means that all have uniform distribution. That is, we don't have really any preference to anyone. That means we don't really have any knowledge about occurrence or non-occurrence of any of the events E1, E2, En. So this is one which is your probably the maximum uncertainty here. This is uniform distribution. For this, probably I can add one more thing, that Those who are interested about all those stuff probably see the book by Jane Kapoor. Jane Kapoor has written one very nice book on probability, your entropy maximization. People try to maximize the entropy because of different reasons. I will come to this within a short while. But the thing is that if I see that, if I consider this your continuous distribution with support from 0 to infinity, say for some given mean, then we will see that exponential distribution is the one which has the maximum entropy. But if my support is from 0 to infinity, minus to infinity over the whole real line, continuous distribution again, and we give that its second moment is given, then we will see that the distribution which will have the maximum entropy subject to that particular condition is normal distribution having variance sigma square. It could have any mean. So normal distribution with any mean will have the same entropy as long as the variance is the same. Now I will come to this your at the very beginning we told about your system, that every system tries to go to the equilibrium where the system will have maximum entropy. This eventually has something to do with your central limit theorem. You know that if xi's are independent identically distributed random variables with mean 0 and variance 1, any random variable with mean 0 and variance 1, and we consider x1 plus x2 plus xn over root n, then as n tends to infinity, this will converge to n01. That is what is central limit theorem. This eventually comes from this entropy thing. The reason is that if I define x1 plus x2 plus xn by root n, which is going to n0 and 1 as n tends to infinity as Sn, then it can be shown that Sn has, for every finite n, Sn has the entropy which is less than the standard normal distribution with mean 0 and variance 1. So maximum normal distribution has maximum entropy, and since every system will try to get its entropy maximized to come to the equilibrium. So once you see, that's what exactly we see in central limit theorem, that Sn converges to normal 0, 1 as n tends to infinity, because this is eventually where it will stabilize. Here, one thing we have to see that HP, whenever I write function, then whatever we write here, that becomes your domain. Your argument. But here it is not the argument, as it is given here that here P is not an argument but a level, because here P is P1 P to Pn. If I have Q as some Q1 Q to Qm, then we will write this as HQ. This is the way the notation we will use throughout. Now you have seen the couple of postulates we wrote at the very beginning, starting from the very conceptual thing. And we got Shannon entropy, but actually Shannon in his original paper in 1948 did not use all those postulates. Actually, Shannon used these three postulates to get the entropy, whatever we know as Shannon entropy. Alfred Rennie in 1961, he has shown that different sets of postulates will characterize Shannon entropy.
पढ़ावा लोने ना
हेलो
सही देखा लोने जी ना पार्टिसिपेंट यो वाला तीक भी आ गया ऑनलाइन
1 minute
यो किसने मैसी
please the participant, hello, please the participant is requested not to say anything. Please mute your microphone, please. Please.
Alfred Rennie in 1961, he has shown that there are different kinds of postulates possible, which will eventually generate Shannon entropy. And two we have already seen. One we have derived using a set of postulates. One Shannon has already given, and one is given here. That here are 4 postulates. These will again generate the same entropy. And just you see this one, this D1 we are going to change now, keeping A, B, and C fixed. This is what is called a direct probability, direct product of two distributions. That P1 is your P1 P to Pn, and Q is your Q1 Q to Qm. then direct product is P star Q is Pi Qj. So we multiply all Ij, and Reni has replaced this D by the D star. That H P star Q is HP plus HQ, and he has shown that many quantities other than Shannon entropy will satisfy A to C and this D dash. That means again different kinds of entropies are possible keeping these 4 postulates. And one is here which Reni has derived, and this is eventually known as Reni entropy in the literature. So any Reni entropy as alpha tends to 1, we get Shannon entropy, and when if we allow alpha to be 0, then HP will reduce to log n, the cardinality of the vector P. This is what is called known as Hartley entropy, and Hartley has shown that the only function is Hn log n with base 2, which will map from n to R satisfying these 3 postulates. Mn is Hm plus Hn, Hm is less than equal to Hm plus 1, and H2 equal to half. That was derived in 1928. Your 20 years before this Shannon entropy came to picture. Reni entropy is actually, just to try to see the difference, this was your Reni entropy here, and you will see a little bit of difference of this. This eventually, Reni entropy was defined by this. Reni did this thing. Here, this sigma pi need not be a probability distribution, because this need not be your 1. If sigma pi is less than equal to 1, even less than 1 will work, no problem. With all pi is positive, then also this thing will come. That's what Reni has shown. But in our discussion, we will take sigma pi to be 1, your complete probability distribution. R.S. Verma, he has again generalized Reni entropy in 2 different ways. And once you just see this thing and try to see what is there in your Reni entropy, you will see that simple reparameterization will give these 2 from Reni entropy. So as a result, this Verma, whatever has done, is really nothing new over Reni entropy. He has given this argument that your this reparameterization is required because here your parameters will not be your proper fraction. Okay, but in Reni entropy, this is a proper fraction. But even if it is proper fraction, what is the problem? He has not discussed in his paper. This is the paper he has published in 1966, and the reason he has given like this. But what exactly is the problem if your parameters, as in the Reni entropy, this alpha is not integer, then what will happen? Nothing is discussed over there. And at least from my knowledge, I don't see any problem in that. Harvey and Charvert, they had in 1967, has again derived on entropy. This is known as structural alpha entropy based on these postulates. So there are different postulates, and they have worked on this. And now the important part, entropy on continuous random variable. Here Hx, there it was sigma minus sigma pi log pi. Here simply pi has been replaced by corresponding density function. So mass function has been replaced by density function, and sum has been replaced by integral. So this is your continuous random variable, Shannon entropy for continuous random variable. And similarly, this is for Reni entropy, and other entropy also you can just simply write. You just replace your sum by integral and your mass function by density function. Then it will come. But some problem we will see in this continuous part of Shannon entropy. We'll come to that later. But Khinchin has generalized this by taking one convex function g, where g1 equal to 0. So gx equal to minus log x will give you Shannon entropy. This is another kind of generalized entropy known as H5 entropy by this Pardo and his group. They have done in 1995. This is generalized in the sense that so many things we will get by taking different hx and phi x, Shannon entropy, Reni entropy, Shannon entropy, Reni entropy, your Verma's 2 entropies, and some more also will get from that. That's why this Shannon entropy, at least mathematically, it's generalized over others. Cruz and his team, they have used Reni entropy in physics, information theory, engineering, and different other fields to describe nonlinear dynamics and chaotic system. But I am not interested in this particular thing, but this the second one, it is more important, that Reni entropy as a function of alpha has been used by Song, and this is called spectrum of Reni information that we will use. you see that log likelihood and Renyi entropy, this is fx, this f is the density, x is my random variable. So I am taking variance of that, and this relationship can be easily proved. This h alpha x is the Renyi entropy. If I call this variance of log fx as SF, then we see that SF is Sg for every relationship like this. This clearly tells that this particular SF is independent of your location and scale parameters. Once it is location and independent of location and scale parameter, we can use this as a measure of kurtosis. Here I would like to tell a couple of things about kurtosis. The thing is that generally in your classical statistics, people use kurtosis, which is eventually your fourth measure over your square of say your variance minus 3. That is used as a measure of kurtosis. And actually, in classical statistics, people consider this as a measure of pickedness. But unfortunately, this does not measure the pickedness of a distribution. It only tells that how heavy the tails are. That we will see very quickly. And if we consider this as a measure of tail heaviness, as we do by your fourth moment, then one thing we will see that for distributions for which this moment, fourth moment, or even second moment does not exist, for that distribution also we can use this SF as a measure of tail heaviness. That we will see very quickly. Here you see the tail heaviness. If you see your what is beta 2? Beta 2 is eventually that measure, mu4 by mu2 square. Mu4 by mu2 square. And if we consider mu4 is my fourth moment and fourth central moment, and mu2 is my variance, we see that for Laplace distribution, and this is my T distribution with 6 degrees of freedom, they have same beta 2. This clearly tells that as far as the tail heaviness is concerned, they should have the same kind of tail. But this is not the case if I consider this thing. That if I consider the SF, then for T6, the SF is coming out to be this, and for Laplace, it is coming out to be 1. That clearly tells the Laplace distribution has heavy tail compared to this. Now the question immediately comes, can we see that this actually can be taken as the measure? That we will see right now. Just try to understand these two things. This is telling that the tail of the two distributions, they are same, and this is telling that Laplace distribution has heavy tail. And just drawing these two curves, we see here that this red one is Laplace. So Laplace distribution here, you see that it eventually has your heavy tail compared to your T distribution with 6 degrees of freedom. Here is one distribution, Cauchy distribution. This distribution actually, if you just simple integration will tell you that this distribution does not have any moment because moment here does not exist. So here you just cannot check this distribution at the end, this distribution which has heavy tail by your moment measure. But here you can see that Cauchy distribution, this your S measure is 3.2. Here it is 4. That means Kramer distribution has heavy tail compared to your Cauchy distribution. Anyway, now we will quickly tell a couple of your comments, rather your drawbacks. Awad has given one example. You see this example. P is this. This is one P vector. And here the contribution of P1, contribution in the entropy, if I consider entropy of this thing, that is P log P minus P log P. So I have just removed minus. So minus log P this and minus 0.5 log 0.5, they are eventually same. Although the probabilities are different. So P1 and P3, they are different, but the contribution in terms of entropy, Shannon entropy, is the same. What does this mean? That means entropy of a system as weighted average, whatever we have taken, this sigma Pi log Pi eventually your weighted average of the entropies of the components, it's not correct way to define entropy. That's what is observed by Awad. This is another example that here it is my P, here it is my Q. You can see that P is not equal to Q, but PQ is HP is same as your HQ. That means distributions here are not identifiable in terms of entropy. This is another drawback of Shannon entropy. If I consider discrete random variable, then your minus Pi log Pi will always be your non-negative. But if I take continuous random variable with uniform distribution AB, you will see that this becomes negative when B minus A is less than 1. So here negative your entropy is becoming negative. If I see here just linear transformation, you see that measuring some characteristics in two different units should not change the obtained information. What does this mean? That means I have this x is suppose measured in centimeter, y is measured in say meter, but their entropy should have been same because I have not done anything wrong. But here I see that if it is a continuous random value, say height or something, then I see that the entropy is different, which eventually violates the your principle that in which way you measure the entropy or the your uncertainties should remain the same. This is not the case here. So Awad, and after that your Ajam and Awad in 1965 and here in 1967, they have proposed two different ways of defining entropies. And this is eventually some way, new way of defining entropies, where the drawbacks of Shannon entropies can be removed. Now the question comes, entropy, whatever you have seen that integral, if you see this, your continuous random variable, then your entropy of a continuous random variable becomes minus integral 0 to infinity fx log fx dx. That means support is my 0 to infinity and I am integrating from 0 to infinity. That means I am considering some new item. If I have some used item, how to define entropy? This is done here that given that x is greater than some time t, that means this, suppose this is the life of some system and given x greater than t means this system has survived from some t units of time, then x minus t given x greater than t is eventually the remaining life of the system. So in case of capital X, I can, or the random variable, I can replace this by xt, and once I do this, this becomes your residual entropy, and this can be used for any used item. The item which are used for some t units of time, this will become entropy for that. This is eventually your Shannon entropy for that particular used item. So using that, people have your generalized a lot of things from here that you can generalize this in case of Shannon entropy, you can generalize this for your Renyi entropy, you can generalize for some other entropy. Very few entropy we have discussed so far. One is what is called Sally's entropy. Sally's entropy is one which is used a lot in physics. Okay, so different other entropies you can get. Here in 2004, Rao and his team, he has defined this kind of thing. I will consider only this one because if x is my non-negative random variable, then this will eventually come to this. Just try to see this. What is this? That means here I have density function. Here this has been replaced by probability x greater than x, and here also probability x greater than x. That this we call the your reliability function, and so density function has been replaced by reliability function to get rid of this negativity thing, because here whatever be the case, your f bar is always less than 1, so as a result this is always positive. So here entropy cannot be your negative. But Rao has given a lot of your reason for doing this, and the reason is that he has told that probably for continuous and discrete, for both the cases you can use it. True, that can be done. He has also told that this particular entropy, whatever he has defined, possesses a lot of mathematical properties than Shannon's entropy, which is also true. And once we have a lot of your mathematical properties, then we can use it in different places with flexibility. Sample data, once you have, then your calculation of this in terms of sample data is much more easier compared to Shannon entropy. That is again true because there you have density. Density estimation from data is not that easy, but here I can simply, f bar x is a proportion. So I can simply use my proportion in place of your f bar x, and this can be your obtained as estimate from the data. So estimation also, for estimation purpose, this is also again very, very true. And after your doing all those stuff, we can see that this asymptotic property or of this particular your entropy, this in your for a large sample, this will asymptotically converge to the true value. That also he has shown. Okay. And another very important thing is there are a lot of distributions for which density does not exist, because if the random variable is not absolutely continuous, then density will not exist. And for the distributions which are not absolutely continuous, Shannon entropy cannot be defined because density does not exist. But this can be defined even if the density does not exist. So all those things are your positive thing for this your residual entropy. Different other kinds of entropies are done. This, as I told, that cumulative residual entropy, all those things you can. This past entropy is something like this, where F bar is replaced by capital F. This was my probability. F bar X is probability. So this is F bar T is probability that the random variable X is greater than T. This capital F is 1 minus F bar. Okay, so people have used F in place of F bar and done a lot of things. So these are some of the things I have written. But now the most important part here I want to tell is that all those things have been done very mechanically, because from small f, Rao has replaced it by capital F bar. Now you are using capital F. Here is another generalized cumulative residual entropy. People have used this, people have used that, lot of things. These are for mathematical purpose, probably it is that is good. I don't mind. It has a lot of different properties. People have studied all those things. But the thing is that whether these are really very useful. I at the very your title I told that your remedies I have given. I will stop by telling one, as I promised, that I will give you some problem to think of on this. And before that, this is probably you can see, this is eventually your, this has, as you can see the title, that this eventually tells you different kinds of entropies on your statistics, reliability, information sciences, whatever people have done from 1942 to 2018, they are summed up over here. And whatever is done in statistical inference, again, during this period, this is as it is written in the last 7 decades, that will be published here in International Statistical Review Journal. Now we'll stop by giving one open problem. It is, I should not say really open. It is really some one interesting problem. Just to try to understand. At the very beginning, Shannon entropy, your Rennie entropy, then your different other entropies, for spectral entropy, all those things, whatever we have defined, there were certain list of your postulates behind it. But once we have discussed all those things, these or even all those things, here, starting from here to here, there we don't have any postulate underlying this. So I ask the new generation to think of that, just start from here. Suppose this is one entropy given. What are the postulates that will eventually give this entropy? This is not yet known. And people really, it is, I am not interested to, although I have typed it open, but it is, I don't want to tell it an open problem, because I don't think that people have really thought of this kind of thing. The thing is that let me take one entropy, which is available in the literature as some kind of generalized entropy, take this and try to set some postulates, starting from those postulates whether we can get this entropy. If we get this entropy, then definitely these postulates are behind this entropy. This is first work. Once we do this, then immediate things come that whatever entropies we have, whatever postulates we have framed to get this particular entropy, say whether all those postulates are really feasible, because entropy we will use in practical sense. So whether the postulates which will lead to this kind of entropy, whether they are feasible or not. If they are not feasible, then definitely we have to change a little bit, or we have to divert a little bit from these postulates, and we have to make a set of postulates which are eventually feasible, by making as less changes as possible on this particular set which gave you this particular entropy. Now, once these changes you have done, then definitely you cannot tell that this changed set will again give you this entropy. It may not be so. Then start from this changed set of postulates and try to get what entropy eventually you are getting. And if you get that, that will really be a very good work, and that definitely people will appreciate. Okay, thank you very much.
Thank you, sir. Thank you for your quite knowledgeful lecture. Now, may I request Professor Anindita Mukherjee to kindly place some selected questions put forward by the participants to Professor Nanda. Anindita, are you here?
Yes, sir. Yes, sir.
Please.
Good afternoon, Dr. Ashok Nanda, sir. Myself, Anindita Mukherjee, and I would like to read out some of the questions from our participants. So the first question that they asked was, what is the geometrical approach of this Shannon entropy?
Okay. Geometrical approach is actually there. Right now, I don't have this particular paper to show, but the thing is that this is freely available paper. Just give a search on Shannon entropy, or you can go to this Beltech journal. Just find this your Shannon entropy 1948. You write that, one paper will come. It is a really one huge paper. Huge number of pages are there, and there you will get. That is discussed there. Shannon has eventually discussed all those things there.
Okay, sir, thank you. The next question that we got was, what do we actually mean by tail heaviness?
Oh, tail heaviness is, as I showed this picture, that tail heaviness, if I know, I mean, just your take any distribution, take either left side or right side. So tail, if I have your one distribution going all the way to infinity, then its tail will also go to infinity to the right side. And if it is starting from minus infinity, then your one tail will go to the left. Okay. By tail, I mean, once I am going towards right or towards left from the middle, then if we have two distributions, and if I draw the two distributions and we see that one distribution has, just to see the diagram of the two distributions, and you see that your one tail, the right side, one is dominating the other, one is at the top of the other, then which one is the top? Definitely its tail is heavy.
Okay, sir, thank you. I hope that our participant has got his query answered. The next question was about the physical significance of negative entropy.
Actually, negative entropy as such, you don't, if you see, you will not get what is called that way physical interpretation. But negative entropy has been used by long back by Schrodinger in physics. And Schrodinger has one very famous book. The book is What is Life? This is the title of the book. There eventually he has used a negative entropy, but in our place, this negative entropy really does not mean anything. But this negative entropy later has been known as negentropy. Negentropy. And this negentropy is defined as the measure of distance to normality. If I am away from normal distribution, then how far I am away from normal, this distance is measured through negentropy.
Okay. So the next question was, which entropy is more suitable for the complexity and risk analysis of the time series?
Very difficult to tell because I cannot tell even a single entropy that way, because if you try to see that Shannon entropy was used a lot. Even after that, Renyi entropy has been used a lot by physicists. Now, recently, what I told, the Salish entropy, people are using Salish entropy in different fields. Okay. The thing is that what you have to do is you have to see the problem, and I can tell you something. Suppose you have some data. From that data, you take certain portion of the data and use that data for particular, you take one particular entropy and use that particular data to your estimate the entropy, and try to use the remaining part of the data and see whether your whatever you have estimated that works for that. Okay. So this is your what is called validation. That way you can see which probably can be the best one to use. In general, it is very difficult to tell. That depending on your situation, you have to decide that this is the given situation, and this is one your prescription, that this is one you will use for this all kinds of data. That is not possible. Had this been there, then probably people would not have thought of different kinds of entropy. So this is not possible.
Okay, thank you, sir. And the final question that we are addressing today is, what do we mean by entropy maximization?
Well, entropy maximization is something like this. Suppose, let me take this example of normal distribution. As I discussed, that normal distribution has your maximum entropy for your all continuous distribution. Among all continuous distributions, with support R and a given your second moment. Okay. If you consider your normal distribution, then normal distribution will have the entropy 1/2 into 1 plus log of 2 pi sigma square. This is the entropy of, you see the expression, I am telling 1/2 into 1 plus log of 2 pi sigma square. That means there is no, the sigma square is given, but not the mean. That is, whatever be the mean, all normal distribution will have the same entropy here. By entropy maximization, we mean that suppose I have a continuous distribution with support over R, then what will be the entropy? Entropy will be minus integral fx log fx minus integral fx log fx dx. Now, here I am integrating over minus into infinity. That I can integrate if one particular f is given. If f is not given, then I cannot integrate. So the constant here is given, the variance is sigma square. So simply we have to maximize minus integral fx log fx dx plus lambda times, this is your Lagrange's multiplier, plus lambda times your second moment minus this given sigma square. Okay, this is your constant maximization problem. So we have to now maximize this with respect to f. Take different f which are continuous, having support over minus into infinity, and try to maximize all those. Once you maximize, then you will see that that normal distribution is the one which satisfies all those things and has the maximum entropy. Here, if you see that it eventually it will like there are infinite number of your small f available. So how I will try? No, this trying business will not work. And there are different techniques for doing that. As I told at the very beginning, that there is a book by J.N. Kapoor, Maximization of Entropy. You just, or entropy maximization problem or something like this. Okay, just give maximum entropy by T.N. Maximization of entropy by J.N. Kapoor. You will get that. Okay, there are different, this is a very huge volume book, not a very your small book, it's a very huge volume book, and there are different techniques of handling maximization problem, entropy maximization problem have been discussed.
Okay, so one more question that has been posted was, what do we mean by generalized probability distribution?
Oh, generalized probability distribution is a probability distribution is sigma my P1, P2, Pn, for example. This is a probability set of probabilities. So discrete probability distribution P1, P2, Pn. So what is Pn? A random variable is x which takes values x1, x2, xn, say. Then probability that the random variable will take the value x1 has probability P1. It will take the value x2 probability P2, and it will take the probability value xn with probability Pn. So for probability distribution, we know that all those PIs, P1, P2, Pn should be greater than or equal to 0, and sigma PI should be your 1. If we encounter some situation where sigma PI is not equal to 1, it is less than 1, what does this mean? That means the random variable x can take some value beyond x1, x2, xn, which is probably not known to us. In that case, obviously your sigma pi will be less than 1, and this kind of distribution where x takes value x1, x2, xn, and something more we don't know, with two different probabilities P1, P2, Pn, P1, P2, Pn, they are positive or non-negative with sigma pi less than 1. This kind of distribution is called generalized probability distribution.
Sir, hello.
Yes.
I am Debrajnath from Thakurpukur Vivekananda College. Sir, I have a question about cumulative probability density function. Can you see your slide where you define the generalized cumulative probability entropy?
This one?
No. Generalized cumulative entropy.
Generalized cumulative entropy.
You have defined, I think, 1 by factorial n fx minus log of fx whole to the power n dx.
This one.
I can see just one slide, an open problem, but I cannot
that
see
slide
this
is
problem.
not visible. That slide is not visible.
Okay.
Okay, I think
sir,
sharing is, wait. It is showing that sharing is paused. Probably that's why you don't see. Let me try it once again.
Yes, sir. Yes.
Yes. Here it is defined that the generalized cumulative entropy. But I have found a paper where the generalized cumulative probability entropy is defined as a replaced probability by the distribution function.
That's what actually what I call is this cumulative past entropy. Here it is F bar is replaced by capital F.
Capital F bar is your distribution and F is a density
capital,
function.
No. Capital F bar is actually 1 minus distribution function. Capital F is my distribution function. So what I am trying to tell is, let me go above. Here, this one. Here you are telling that this capital F bar is replaced by your CDF, right?
Yes.
CDF means continuous probability density function.
Not probability density function. It is cumulative distribution function. Probability x greater than x.
Oh, distribution function replaced by density function.
No, earlier we started with Shannon entropy, where we had your. Let me quickly go to your. I think it is quite. Yeah, no, it is not. This is here.
This is the density function.
This is the density function. This density function has been replaced by your probability. This fx, small x, is replaced by the random probability that the random variable will be greater than x. That has been replaced by Rao in 2004. That's what I showed right now. After that, people have used this small f was replaced by your 1 minus capital F. Now people have replaced this small f by capital F also, which is my cumulative distribution function. That's in the literature is known as cumulative past entropy.
Cumulative past entropy. But I have found one paper there, probability x less than equal to a is called the cumulative probability density function.
Yeah,
and
this is cumulative.
A is called as.
This is probability x greater than equal to x, whatever probability that capital X is less than or equal to x. This is called cumulative distribution function.
Cumulative, and complement is called the survival distance function.
Survival function. This is called survival function. This is
Okay,
called
but,
survival. The reason is very simple. This is called survival because if x is my some item, then x is greater than x means, or x is greater than say t, say x is greater than t, means that the random variable x is life of some system, and x is greater than t means the system has survived at least for t units of time. That's why this x greater than t, this probability is called reliability or survival function, because it has survived for t units of time. That's why it is called survival function.
Okay, I have a second question. For discrete continuous probability distribution, all the postulates are satisfied. But in continuous probability distribution, there are some problem occurred where the mainly occurred for complexity analysis. Some of the postulates are not satisfied. For example, if I choose a distribution function is an uniform distribution function 1 by b, where b greater than 1.
Yeah, this is sometimes it becomes negative, sometimes it does not satisfy the your postulate. Yes, this is there.
Okay, so in this case, can you provide some information?
Excuse
How
me,
can you
Mr.
overcome
Nath.
this?
Hello.
Hello.
Excuse me. Actually, our next speaker is already waiting. So we'll be very much grateful to you if you kindly put your questions in the mail ID of Professor Nanda. We can provide you the mail ID so that you can discuss with him.
Okay.
Sorry for the, actually our next speaker is already waiting. Sorry for the interruption.
No problem. Thank you.
Thank you. We are giving you the mail ID in the chat box. So, Dr. Amit, please proceed.
Thank you, sir, for
You're
your lucid presentation. From your valuable time you have given us. Thank you.
It's my pleasure. It's my pleasure to be with all of you.
Thank you, sir. So, come to our next session. Our next speaker is Professor Shantanu Shahare. Dr. Shantanu Share, professor and head, now currently working as head of the Department of Mathematics, National Institute of Technology, Rourkela. And his topic is high order numerical methods for risk fractional partial differential equation in anomalous diffusion modeling. Now, before his presentation, I want to give a brief biography of Dr. Shantanu Share. Dr. Shantanu Share is currently a professor and head of Department of Mathematics, National Institute of Technology, Rourkela, India. He has completed his bachelor degree in mathematics honors at St. Xavier's College. It is currently known as St. Xavier's University, Kolkata. He completed his master's degree in applied mathematics, Calcutta University in 1998. He received his Master of Computer Application degree in 2001 from Indian Institute of Engineering, Science and Technology, Shibpur. He awarded his PhD degree from Jadavpur University in 2008.
Charon Sundar, English Sundar, Darun presentation, smart presentation, for a seminar.
Madam, please, madam.
Darun Sundar.
Madam, Anindita, madam. And for Dr. Shantanu Share was elected fellow of the Institute of Mathematics and in Application, United Kingdom in 2018. Dr. Share has more than 20 years of teaching experience at the undergraduate and postgraduate levels in glorious institutes like National Institute of Technology, Rourkela, and two renowned private engineering institutes in Kolkata, West Bengal. He has more than 19 years of research experience in various fields of applied mathematics. He has published many peer-reviewed research papers in numerous fields of various international SCI journals of repute. He has more than 180 research papers published in journals of international repute, including more than 149 SCI journals papers. He has awarded an IOP Publishing Top Cited Author Award 2018 from India in the field of physics, published across the whole IOP publishing portfolio in the past 3 years, 2015 to 2017. He has solely authored a book entitled Graph Theory with Application and its Application in Applied Science and Technology, published by Spinger. A solely authored book entitled Fractional Calculus with Application for Nuclear Reactor Dynamics has been published by the CRC Press of the Taylor and Francis Group. Another solely authored book entitled Numerical Analysis with Algorithms and Programming has been published CRC Press of Taylor and Francis Group, USA. Another 3 books entitled Wavelet Methods for Solving Partial Differential Equation and Fractional Differential Equation, Generalized Fractional Order Differential Equation arising in physical models, and Novel Methods for Solving Linear and Nonlinear Integral Equation has been published by CRC Press of Taylor and Francis Group, USA. Recently, his book entitled Nonlinear Differential Equation in Physics has been launched Fringer Nature. Currently, he is acting as an editor-in-chief of the Fringer International Journal entitled International Journal of Applied and Computational Mathematics. He is also an associate editor of the Springer SCI Journal, Mathematical Science, and reviewer of several journals of Elsevier, Springer, and Taylor and Francis, etc. He had also been the lead guest editor in the International SCI Journals of Hindoi Publisher Corporation, USA. He has contributed papers on several topics such as fractional calculus, mathematical modeling, mathematical physics, stochastic modeling, integral equation, and wavelet methods. He is a member of the Society of Industrial and Applied Mathematics, that is known as SIAM, and the American Mathematical Society, AMS. He was the principal investigator of 2 broad of research in nuclear science research project with grant by Bhabha Atomic Research Center, Mumbai. He was also the principal investigator of the research project financed by the SARB Department of Science and Technology, Government of India. and a research project financed by NBHM, Department of Atomic Energy, Government of India, respectively. Currently, he has been acting as a principal investigator of research projects financed by SARB, Department of Science and Technology, Government of India. Under his sole supervision, 4 research scholars had been awarded with PhD from NIT Rourkela. Recently, 1 research scholar submitted his thesis and currently is supervising 8 more research scholars. He has delivered different topics of lectures from different institute of international national repute and many more. Professor Sahare, this is the short biography of Professor Shantanu Sahare. Sir, please, we invite you for your topic, for your presentation. Thank you, sir. Sir, please.
Okay, thank you. First of all, can you hear me?
Yes, sir. Yes, sir. You are audible.
First of all, I would like to thank Professor Pal for kind introduction. It is my immense pleasure to join this webinar. I would like to thank organizing committee to organize such a wonderful webinar. Also, I like to thank Principal Sir for invitation to present my lecture. I welcome everybody for attending my webinar presentation. So let me first share my slide. Is it visible? My slide is visible to everybody?
Yet not.
Hello?
Echono not.
It is not visible.
No. It is opening.
Now?
No.
Is it visible now?
No.
The file names are coming, sir. The file names.
Now is it visible? Hello?
No.
What is showing?
Only the files are visible.
Now is it visible?
No.
Now, sir, you have to double click on the file name.
Is it visible now?
No.
No, sir, clearly not visible.
You are sharing your screen, but the PPT is not visible.
Clearly visible.
Now is it visible?
No. I think the PPT is not opening.
The PPT is opening. Now is it visible?
No, sir, PPT is not open. Amit, check it.
Sir, please open the PPT and then, sir, share the screen.
PPT. পিপিটির উপরে ডাবল ক্লিক, হ্যাঁ।
Sir, please open the PPT, then share the screen. Yes, sir.
Yes.
Is it visible now?
Yes, sir.
Yes, visible.
Yes.
Yes, it is visible.
Okay, thank you everybody. The title of my lecture is High Order Numerical Methods for Rich Fractional Partial Differential Equation in Alumnus Diffusion Modeling. Myself, Dr. Shantanu Saharai. I am Professor and Head of Department of Mathematics, NIT Rourkela. The first, let me introduce the outline of my lecture. Is it visible? Outline?
Yes.
Okay, so first I want to introduce briefly what is fractional calculus and some relative illustration. Then I will give the motivation of high order approximation. Then I will move on to numerical methods for solving rich fractional diffusion equation. Then numerical methods for solving time-rich fractional Fokker-Planck equation, then higher order numerical methods for space-rich fractional differential equation, conclusion, etc. Next is, what is fractional calculus? So before I start my actual topic, first I want to introduce the basic knowledge about the fractional calculus. So all of us, we are familiar about the normal derivative and integral. So this is Dept is the first order derivative of f, function f, d2f dt square is the second order derivative of the function f, and integral 0 to t fu du is the integral of f. This is first integral. Similarly, we can get second integral, double integral, which is called double integral. So these are the first order, second order, first integral, double integral of a function. But if we wish to know what is the half order derivative, or pith order derivative, or what is the complex order derivative, then we need fractional calculus. So fractional calculus implies derivative and integral of arbitrary real or complex order. So like a classical integer order calculus, fractional calculus is also old. It was born in 1695. There is a history behind it. So in a letter, L'Hopital asked Leibniz what is the order of the derivative, half order derivative. So Leibniz wrote in his reply that it will lead to a paradox from which one day useful consequence will be drawn. This letter of Leibniz was sent on 30th September 1695, and that date, 30th September, is considered as the birthday of fractional calculus. So these are the main contributors, although there are so many researchers working on fractional calculus. So among those, the main contributors are Leibniz, Euler, Lagrange, Laplace, Fourier, Abel, Liouville, Riemann. They contributed definition of fractional calculus, different definition of fractional calculus. So I have some work on fractional calculus. These are the list of this book. Among these, the last one was published in 2020, January 2020. It was launched by Springer, and I am very much optimistic about the popularity of this book. So nonlinear differential equation in physics. Now, what is successive differentiation? We know the nth order derivative of t to the power n is factorial n. And what is nth order derivative of t to the power n, where n is greater than n? That is factorial n by m minus n factorial t to the power m minus n. Now, if we replace the factorial by gamma function, then factorial n can be written as gamma n plus 1. Then the nth derivative of t to the power n can be written as gamma n plus 1 by gamma m minus 1 minus n plus 1 into t to the power m minus 1 m minus n. The gamma function is defined for positive and negative real numbers, except for negative integers and 0. So here we shall take n and m are real numbers. Now, what is the alpha order derivative of t to the power mu? Is it visible? Is the slide is visible to everybody? Hello?
Yes, sir. Yes, yes.
Okay. So what is the alpha order derivative of t to the power mu? Here mu is greater than -1, remember. Then it is given by gamma mu plus 1 by gamma mu minus alpha plus 1 into t to the power mu minus alpha. This property is known as power law property. Here mu is greater than 1. Not only that, mu is greater than mu alpha minus 1. This condition can be relaxed by mu greater than alpha. Now let us start the some example of fractional derivative. The half order derivative of t to the power alpha can be written as, using this power law property. This power law property given by this equation, we can write gamma 1 plus gamma 1.5. And what is the half order derivative of t? This is t to the power 0.5 by gamma 1 plus 1.5. Now what is the half order derivative of 1? 1 means that mu is 0. Then you can see this is 1 by square root of pi t. But in classical calculus, the derivative of a constant is 0. But in fractional calculus, it is not a 0. It is non-zero. It is rather 1 by square root of pi t. Now, what is successive integration? The first integral of ft is j1 ft. This is integral 0 to t f of u du. The second integral is j2 ft is integral 0 to t integral 0 to u f b dv du. So similarly, nth order integral of ft is given by equation this, and this can be represented by Cauchy, which is called Cauchy integral representation by jn ft. This is 1 by gamma 1 by factorial n minus 1 integral 0 to t minus u to the power n minus 1 fu du. Now if we replace this factorial by gamma function, then we can obtain the Riemann-Liouville fractional order derivative. That is, Riemann-Liouville fractional order derivative we can obtain from this previous definition of Cauchy integral representation. If we replace the factorial by gamma function, then we can obtain Riemann-Liouville fractional integral of order alpha, where alpha lies between 0 to 1. So j alpha ft is 1 by gamma alpha integral 0 to t minus u to the power alpha minus 1 fu du, where t greater than 0. Now, Riemann-Liouville fractional derivative, in case of Riemann-Liouville fractional derivative, first we will take the integral of order 1 minus alpha, then we shall take the derivative. That is, this equation represent Riemann-Liouville integral Riemann-Liouville fractional derivative of order alpha, that is d alpha ft is equal to ddt of j1 minus alpha ft. Here alpha, remember, lies between 0 to 1. What is the corresponding Caputo derivative? In case of Caputo derivative, we shall do simply the reverse thing. We shall first take the first order derivative, then we shall take the Riemann-Liouville integral, fractional integral of order 1 minus alpha, given by this equation. Next is, what we can notice from the fractional derivative, we can notice that fractional derivative involves an integration, and we know that integration is a non-local operator. So fractional derivative is a non-local operator, and calculating the time fractional derivative of a function ft at some time t equal to t1, we require all the past history. That is, we require all the function values of ft from t equal to 0 to t equal to t1. So fractional derivative can be used for modeling the system with memory. Similarly, whenever we calculate the space fractional derivative of a function fx at x equal to x1, we require all the non-local values of fx. So fractional calculus consists of fractional integration and fractional differentiation. So the fractional integral mainly we can say the Riemann-Liouville integral, and there are many definitions on fractional derivatives. More than 6 definitions are there. Although there are many definitions of fractional derivative are available in literature, which are not mutually equivalent. Among those, only Riemann-Leibniz and Caputo derivatives are mostly used. These are the mathematical definition of Riemann-Leibniz and Caputo derivative that I have already explained in my earlier slide. This third equation represents the Caputo derivative, the relation between Caputo derivative and the Riemann-Leibniz fractional derivative. So here the involved integral is Riemann-Leibniz integral j alpha xt given by this equation. Here alpha is a positive real number. So we can say that fractional calculus is taken to be granted as a mathematical generalization of the calculus, but it is not always true. Why? Because if we take the alpha order Caputo derivative, then we can see when alpha tends to m minus 1 right hand limit, then the Caputo derivative of alpha will be m minus 1 derivative of xt. Not only that, another term will come, that is m minus 1 derivative of xt at the time t equal to 0. And on the other end, the alpha order derivative of xt when alpha tends to m left hand limit, that is a derivative of xt. That is no problem. But in case of alpha tending to m minus 1 right hand limit, then it will not only the m minus 1 derivative of xt, but another term will come, that is m minus 1 derivative of xt at t equal to 0. So classical derivative is not the direct consequence of Caputo derivative. So classical derivative is not the special case of Caputo derivative. So fractional calculus, although it is closely related to classical calculus, but it is not the direct generalization of classical calculus in the sense of rigorous mathematics. So for more details, we can consult with my book with my student, Professor Subroshan Sahu, who is now working on KIT University. This is a generalized fractional order differential equation arising in physical model. So let me introduce some illustration on fractional order differential equation. This is time fractional diffusion equation given by this equation, alpha order derivative of uxt equal to second order derivative of uxt with respect to partial derivative t. Now, to solve this kind of equation, it is essentially to know the definition of the function meter Laplace function. This meter Laplace function is very essential for the study of fractional calculus. So because in most of the case in the analytical solution of fractional order differential equation, that solution can be expressed by meter Laplace function. So this is the definition of one parameter interfraction meter Laplace function. Although two parameter interfraction also meter Laplace function is also there. So this is the definition of one parameter meter Laplace function, which is summation over k from 0 to infinity. This is actually infinite series, j to the power k gamma alpha k plus 1, where alpha greater than 0. You can see when alpha equal to 1, this is nothing but an exponential series. So this is the time fractional diffusion wave equation. I have solved this equation in my paper, which was published in 2005 in the journal Physica Scripta. For solving this time fractional diffusion wave equation, I have applied Abelian decomposition method, and I have taken this example with initial condition ux0 equal to sin x, where domain is x greater than 0 less than pi, utx0 is 0, and boundary condition is Dirichlet's boundary condition, which is homogeneous boundary condition at the two end, x equal to 0 and x equal to pi. And the analytical solution that I have obtained by applying Abelian decomposition method, that analytical solution can be expressed in terms of one parameter meter Laplace function as uxt equal to e alpha minus t to the power alpha sin x. So you can see this animation. In this animation, you can see the fractional order behavior of time fractional diffusion wave equation, when alpha is lies between 0 to 1, this is called subdiffusion. When alpha equal to 1, this is actually standard diffusion. When alpha is greater than 1 and less than equal to 2, then it is called super diffusion. When alpha tending to 2, you can see the wavy nature of the equation. Next is motivation of higher order approximation. In 1986, notable researcher Lewis proposed a higher order method for the approximation of Riemann-Leibniz derivative, which was published in Siam Journal of Analysis. And in the year 2011, notable researcher Lee Chen-Ia proposed higher order approximation for capital derivative. Now, in my present talk, I shall discuss about higher order approximation of Ricci fractional derivative and corresponding space Ricci fractional differential equation. So this is the definition of Ricci fractional derivative, which was proposed by very famous researcher Shamko in 1993, and this is the derivative, Ricci fractional derivative of the function fx of order alpha, where alpha lies between n-1 and n, where n is a natural number. And from this definition, we can see that the Ricci fractional derivative is a two-sided fractional operator. The advantage of Ricci fractional derivative is it can reflect the past and future memory of the complex system. So this is the left. First one is the left Riemann-Leibniz derivative, and the second one is the right Riemann-Leibniz derivative. Here, a domain of the x is from minus infinity to plus infinity. Now, if the domain is finite domain, if it is a to b, then fractional order derivative, Riemann-Leibniz fractional order derivative, Ricci fractional derivative of order alpha can be represented by this equation. Here, this left Riemann-Leibniz fractional derivative is represented by 1 by gamma n minus alpha del n del x to the power n integral a to x u xi t by x minus xi to the power alpha minus n plus 1 dxi. This is the left Riemann-Leibniz derivative of order alpha, and this is the right Riemann-Leibniz derivative of order alpha. Now, let me introduce some lemma. In this lemma, this is related to fractional central difference derivative of a. Using fractional central derivative, we can approximate the Ricci fractional derivative. So, using fractional central derivative of a, what is the definition? The delta alpha fx equal to summation over j from minus infinity to infinity gj f of x minus jh, where gj equal to minus 1 to the power j by gamma alpha minus 2 alpha by 2 minus j plus 1 into gamma alpha by 2 plus j plus 1. Now, using this fractional center derivative of a, we can approximate the Ricci fractional derivative of order alpha given by minus h to the power minus alpha into summation over j from minus infinity to plus infinity gj f of x minus jh plus order of a square. So order of this approximation, if we approximate the Ricci fractional derivative of order alpha by fractional center derivative, then the order of approximation is second order. Here alpha lies between 1 and 2. Now recently Chelik and Duman in 2012 proposed that if the domain of the function is a to b, then alpha order Ricci fractional derivative can be represented by minus h to the power minus alpha summation over j minus b minus x by h to x minus a by h gj into f of x minus j H. So order of this approximation is, I already mentioned, this is second order approximation. And this is the definition of shifted Growal approximation. So this is proposed by Mishat and Tedjaren in 2006. So this is the definition of shifted Growal formula. The order of this approximation is first order. So let us take a problem in inhomogeneous rich fractional diffusion given by equation 1. Here the initial condition is Wx0 is phi x and boundary conditions are W0t and WLT equal to 0. This is homogeneous boundary condition. Here k is the diffusion coefficient and phi x is the real value sufficiently smooth function. Alpha lies between 1 to 2. This type of super diffusion problem largely arises in the modeling of fluid flow and finance and many other applications. So first we shall partition the spatial domain 0 to the spatial domain is 0 to L. So we shall first partition 0 to L into n number of subintervals by the point XL. XL is equal to LH with the step size H equal to L by M. And the numerical approximation is denoted by WLK. What is WLK? WLK is the numerical value of WXT at the point, at the mesh point XLTK. So first we shall take the explicit finite difference discretization of equation 1. So if we discretize equation 1 by explicit finite difference approximation, then the inhomogeneous rich fractional diffusion equation can be written in given by equation 2. Here the order of the approximation is first order. So since it is explicit finite difference approximation, so WLK plus 1, that is the value of W at the point XL TK plus 1 can be expressed in terms of previous values of W. So the equation 2 can be written in matrix form by given by equation 3, which is UK plus 1 equal to A into UK plus tau into AK plus half. What is UK? UK is a vector, W1K, W2K, Wn minus 1K, and Fk is always another vector, F1K. That values can be obtained by this function, fxt function, this fxt function. So if this Fk is F1K, F2K, Fm minus 1K, and A is a m minus 1 by m minus 1 square matrix. Symmetric matrix, square symmetric matrix. And let us take another example, time space fractional Fokker-Planck equation. This Fokker-Planck equation arises in transport dynamics of a complex system, and here it is a time fractional. This is the time fractional derivative, and here this is the space fractional derivative of order mu. And mu k alpha mu is the anomalous diffusion coefficient. M is the mass of the diffusion test particle. Eta alpha is the generalized friction constant, and v prime x by m. Eta alpha is the drift coefficient. Here vx is the potential function. Here we have taken the external force v prime x. The external force is fx is minus v prime x. So this is the Riemann-Liouville derivative of order 1 minus alpha. When alpha tends to 1 and mu tends to 2, then this time space fractional Fokker-Planck equation will reduce to standard Fokker-Planck equation. When alpha tends to 1 and potential function is constant, it will nothing but inhomogeneous fractional diffusion equation given by equation 1. So to solve the equation 4, this is equation 4, this is time space fractional Fokker-Planck equation, equation 4. To solve this equation, with a non-zero drift coefficient, that is potential function is not a constant. So I have applied fractional center difference approximation along with dual derivative. So discretizing equation 4 by central difference approximation, then equation 4 along with equation 5 and lemma 1 can be discretized given by equation 6. This is time derivative in this equation 6, the time derivative del W del T has been discretized in central difference approximation, and we have taken the fractional center difference approximation for space fractional derivative. So using the equation 5 and lemma 1, the equation 4 can be discretized given by equation 6. Here the truncation error capital T capital E is given by order of tau square plus A square. This is second order approximation. Tau is the time steps, H is the space step. Now omitting the local truncation error in equation 6, we can express the equation 6 in the matrix form given by this equation, that is I plus A0 into u to the power k plus 1 equal to I minus A0 minus A1 into uk minus A1 plus A2 into uk minus 1, etc., etc. And last term is tau to the power alpha k to the power k plus f to the power k plus half. So this is UK vector I already discussed. I have already mentioned UK vector, and 8k plus half vector is given by this equation. Now here AI is the -1 square matrix, and this scheme is actually implicit scheme. And to derive the proof of stability and convergence of the schemes, I have defined a space, function space, capital lambda, capital omega in this form. So next, let us take the example. This is example 1. In this presentation, I will present 3 examples. This is the first example. This is the rich fractional diffusion equation given by equation 7 with the initial condition Wx0 equal to x square into 1 minus x whole square. Where x varies from 0 to 1, and with the Dirichlet's boundary condition, homogeneous boundary condition, W0t equal to W1t equal to 0, and non-homogeneous part fxt is given by this equation. Now using explicit finite difference approximation scheme given by equation 3, equation 7 has been solved, and the exact solution of the equation 7 is Wxt equal to 1 plus t to the power alpha into x square into 1 minus x square, 1 minus x whole square. In this problem, I have solved by explicit finite difference approximation, whose order of approximation is 1, and then I have taken the diffusion coefficient k equal to 1 and time step tau equal to 0.001 and space step h equal to 0.05, and alpha, I have taken alpha equal to 1.5. The figure 1 represents the comparison of numerical solution with the exact solution at the time t equal to 1. In the next figure, figure 2, this figure represents the comparison between numerical solution of Wxt with the exact solution for t equal to 3. And here, the figure 3 represents the comparison of numerical solution Wxt with the exact solution for t equal to 5. From this figure, we can see there is a good agreement between the numerical solutions and the exact solution of Wxt. Look at this animation. From this animation, we can see the behavior of the solution for different fractional order alpha when t equal to 1. When alpha lies between 0 to 1, it shows the sharp diffusion. When alpha equal to 1, it is a standard diffusion. Standard diffusion means it will show the Gaussian nature. When alpha is greater than 1 and less than 2, it will be super diffusion. look at this animation. This is same for t equal to 3. Same, it will show the behavior of the solution, fractional order behavior of the solution for different fractional order alpha. For again, I can say for alpha lies between 0 to 1, it shows the subdiffusion, and when alpha greater than 1 and less than 2, it shows the superdiffusion. So this is another animation for alpha t equal to 5. Can you see the animation? Hello?
Yes, sir. Yes. Yes, sir.
Next is example 2. In this example, I have solved this time space fractional focal plan equation given by equation 8 with initial condition Wx0 equal to k alpha mu into x square into 1 minus x whole square, where x varies from 0 to 1, and I have taken the homogeneous boundary condition. This is Dirichlet's boundary condition between 0 to t. The exact solution of this time space fractional focal plan equation is given by Wxt equal to k alpha mu plus mu into t to the power 1 plus alpha into x square into 1 minus x whole square. I have solved this time space fractional focal plan equation using implicit scheme, that is using fractional space fractional central difference approximation and dual lectical fractional derivative. So using implicit scheme given by equation 6, the solution has been obtained, and figure 4 shows the comparison of numerical solution of Wxt with the exact solution for t equal to 1. In this numerical computation, I have taken the diffusion coefficient k alpha mu equal to 25 and time step tau equal to 0.0001 and space step size h equal to 0.05, and alpha, that is time fractional derivative alpha, have been taken as 0.8 and space fractional derivative mu have been taken as 1.9. Next slide. This is the graphical representation of the comparison of numerical solution of Wxt with exact solution for t equal to 3. So from these figures, again, this is figure 6 represent the numerical solution of Wxt with exact solution for t equal to 5. So from these figures, it can be clearly observed that there is a good agreement between the numerical solutions and the exact solution. So theorem 1, proof I have proved that I have in my paper, which is published in 2017 in the journal Mathematical Methods in Applied Sciences. In that paper, I have proved theorem 1. And theorem 1 says that the numerical discrimination scheme given by explicit finite difference method for the problem 7 is stable under the condition when r is equal to tau by h to the power alpha is less than equal to 2 by k into g1 minus g2 by cos alpha pi by 2. So next is theorem 2. Theorem 2 says that the implicit scheme given by equation 6 for problem 8 is unconditionally stable. Since it is an implicit scheme, it is expected to be unconditionally stable. And theorem proof, in this theorem I have proved that the numerical solution, that is WL n bar, that is numerical solution of Wxt, it converges unconditionally to the exact solution WLT when s tending to 0, h is the space step size, and when tau tends to 0, that is tau is the time step size. Now I am skipping the third order numerical third order approximation. I am directly move on to the fourth order approximation of least fractional derivative. So for fourth order approximation, we need the theorem 4. Theorem 4 gives the least fractional derivative of order alpha. Here the order of approximation is fourth order. using the fourth order, using theorem 4, we can approximate the Ricci fractional derivative of order alpha in this way, where the order of approximation is fourth order. So this is actually, in this case, we have used actually shifted Gruen-Leknikov definition. So using this approximation, fourth order approximation, the inhomogeneous fractional, Ricci fractional diffusion equation given by equation 1 can be discretized by given by equation 9. Here mu1 is given by alpha tau k by 48 into h to the power alpha, and mu2 equal to tau k by 2 into h to the power alpha 1 plus alpha by 12. Here order of approximation, we will see it in the next. I will see you in the next slide. The order of the approximation is tau to the power 2 plus h to the power 4. This equation 9 can be represented in the compact matrix form given by equation 10, which is I plus h into u n equal to I minus h into u n minus 1 plus tau by 2 fn plus tau by 2 fn minus 1. Here I is the identity matrix of order n minus 1. This is actually implicit scheme, and h is mu2 g minus mu1 g plus minus mu1 g minus, here g plus g minus expression I have omitted here. This is g expression. So again, in theorem 5, it has been shown that discretization scheme given by equation 10 and 9, this is implicit scheme, is unconditionally stable. So, and in theorem 6, the convergence is convergence order is tau to the power 2 plus h to the power 4. So let us take the last example, example 3. This is a Ricci fractional differential equation. In this equation, we have taken the initial condition ux0 equal to 0 and homogeneous boundary condition, that is for uxt at t equal to 0 it is 0, and uxt at t equal to x equal to 1 it is also 0. The exact solution of this differential equation is t to the power 2 alpha plus 1 into x to the power 4 into 1 minus x to the power 4. This has been solved by fourth order approximation scheme, implicit approximation scheme given by equation 10 or 9, given by equation 10 or 9. This is equation 10 in matrix form, and this is equation 9. So table 1 represent the maximum error and temporal convergence order and spatial convergence order for different value of alpha. For alpha equal to 1.2, this represents the maximum orders and temporal or convergence order and spatial convergence order. From this table, we can see that for temporal case, it is convergence order is approximately near about 2, and spatial case it is approximately near about 4. Why it is near about 4 and near about 2? Look at these theorems 6. You can see in the theorem 6, the order of the approximation is tau square and h to the power 4. That tau is for time steps and h is for space step. So for that reason, the spatial convergence order is approximately 4 and temporal convergence order is approximately 2. So this table represents the approximation maximum error and spatial and temporal order for different values of alpha. Alpha equal to 1.2, 1.4, 1.6, and 1.8. So figure 7 represents the comparison between analytical and numerical solution for t equal to 0.2 and alpha equal to 1.1 for example 3. And from this figure, we can see there is a good agreement between these two solutions, analytical solution and numerical solution. And again, figure 8 represents comparison between analytical solution and numerical solution for t equal to 0.8, for alpha equal to 1.9. Figure 9 represents the numerical solution for alpha equal to 1.2. This is the 3D surface solution. And figure 10 represent the analytical surface for alpha equal to 1.2. From these two figures 9 and 10, we can see that the 3D surface solution is exactly same. This is another numerical solution, 3D solution for alpha equal to 1.8. And this is the analytical solution for alpha equal to 1.8. So these two solution, 3D solution graphs for figure given by figure 11 and figure 12 are exactly same. So what is the comments? Next is, so we need the proper application and exact application of fractional calculus. And since this is non-local fractional derivative or non-local derivative, so we required effective and economic numerical methods to approximate the fractional derivative. The fractional calculus, along with stochastic process, will characterize our complex world, because fractional calculus is non-local, characterized by non-local nature. And numerical in my future work, my intention is to apply numerical method for fractional stochastic differential equation and many other work I have planned. So if you not yet studied the fractional calculus, now start with fractional calculus. I am giving you some references of my work on rich fractional differential equation. This is the list of references, and this is numerical calculations of rich fractional differential equation. These are related to my work. These are the outcome of my project, research projects. Title of the project was Analytical and Numerical Solution of Rich Fractional Partial Differential Equation. It was sponsored by MBHM, and it was started in March 2015 to March 2019. I was the principal investigator of this project. I also thank to BRNS and SAR DST and obviously MBHM for financial support for pursuing this research work. These are the references of my presentation. Thank you.
Thank you, Dr. Shahare,
Yes.
for your presentation. Nice presentation, which shows the immense knowledge of you in this subject. Now, few questions. I think there are only few questions. May I request Professor Riya Chakraborty to kindly place some selected questions put forward by participant to Professor Shahare. Riya, are you here?
Good afternoon, sir.
Yes.
Thank you so much for your nice presentation.
Thank you.
Now I am asking a few questions from the participants. What is the physical interpretation of fractional order biological model, and what is the appropriate value of discretization parameters?
Actually, biological model, I have yet to apply the fractional calculus in biological model. I have some few works on biological model, but not totally on fractional calculus. It is related on stochastic process, but I have yet to apply the fractional calculus in biological model. Okay.
Hello, Riya. Hello.
Hello, sir. What is the application? Sir, what is the next question? What is the application of the field?
Application I have already shown in my animation. We know all of us we know the diffusion equation, and all of we know the wave equation. Now, what is the nature when the derivative order of the derivative is like with diffusion is when alpha is 1, that is we know the diffusion, and if alpha lies between 0 to 1, what will be the nature of the solution? That the nature can be expressed by that is called anomalous diffusion, and that name of when alpha lies between 0 to 1, the specific name of the diffusion is called sub diffusion. And when alpha equal to 1, that I already mentioned, this is the standard diffusion. This is actually nothing but Gaussian distribution. When alpha is greater than 1 and less than 2, this is another anomalous diffusion that is called super diffusion. When alpha equal to 2, we already know that is represent the wave equation. So this is the application.
Okay. Okay. Thank you, sir.
Thank you.
Thank you. I have a one basic question. What is the difference for which one is the much more applicable, Riemann-Liouville fractional derivative or capital derivative fractional derivative? Which one is the best?
Listen, Riemann-Liouville, one drawback is there in Riemann-Liouville fractional derivative. If you apply the Riemann-Liouville fractional derivative, the initial conditions will be in fractional order. So that is a problem in applying the Riemann-Liouville fractional derivative. On the other hand, if you apply the capital fractional derivative, then the initial conditions will be of integer order. So for practical application, it is better to apply, instead of Riemann-Liouville fractional derivative, it is better to apply capital fractional derivative.
Okay, thank you.
This reason.
Sir.
Thank you.
Thank you once again. Thank you, sir.
Thank you.
Now, in the last part, I invite Professor Amit Sarkar to deliver the vote of thanks. Professor Sarkar?
Am I audible?
Yeah.
Yes.
Thank you, Dr. Pal. Good afternoon, everybody. It's my immense pleasure to share my candidature and convey my vote of thanks. Nothing can be possible without our respected principal, Dr. Ashok Mukhopadhyay. I extended my wholehearted thanks to him. Honorable speakers, Professor Ashok Kumar Nanda and Professor Shantanu Saha Ray are giving their valuable time from their busy schedule. On behalf of college and Department of Mathematics, I convey my gratitude for their presence and valuable lectures. I would like to thank IQSC coordinator Dr. Radhanath Pain and the other IQSC members Dr. Nilashish Pal, Dr. Sudeshna Shao, Dr. Gargi Basu and Professor Debraj Rai for their bright presence and cooperation to make this webinar successful. I also convey my regards and love to the faculty members of Mathematics Department, Dr. Shukdev Datta, Dr. Amit Kumar Pal, Dr. Anindita Basu, Professor Subroto Bhakto, Professor Gauri Shankar De, Professor Riya Chakraborty, Professor Anindita Mukherjee, and other faculty members of this department. Without them, nothing is possible. Especially, I am thankful to all other teaching and all the non-teaching staffs of our college for their support for every program behind the screen. I would love to express my gratitude to all of the participants. Without you, nothing will be fruitful and turn into a grand success. Finally, on behalf of college, I convey my dignity with vote of thanks and conclude the program with my short message. Stay home, stay safe. Thank you for your time.
Thank you. Thank you, Professor Sarkar, for your vote of thanks. Now, for the last session, concluding session, may I request again Dr. Anindita Basu, please, Madam.
Yes.
Dr. Basu, please conclude.
Thank you. Yes. Thank you, Dr. Amit Pal, Professor Amit Sarkar, Professor Anindita Mukherjee, and Professor Riya Chakraborty for nicely hosting the technical session. We are almost at the end of our webinar. It's been immensely satisfying for all of us to be able together in one scientific platform, maintaining strict social distancing and still learning high quality mathematical science from two peers through this webinar. I must thank all of you for taking time out of your busy personal and for your presence. In the end of our webinar, I wish good luck. Thank you. I hope all participants have already filled up their feedback form from the chat box. Please fill up the feedback form from the chat box. It's must, otherwise we'll not get the certificate. Thank you.
रे सब छाड़ी चुड़ा के पड़े मुझे क्लास रे